So, now let us go back to our free energy. So, free energy was function of this continuous variable phi, right, phi squared, grad phi squared, phi 4. So, we have phi field. Now, you imagine, well, please remember that we are working with fields at different scales. Okay. So, we do coarse graining. So, we are basically looking at larger scales. In Wave number space, so in Fourier space, when I coarse grain it, then which waves, which modes are kind of left out, or which modes are averaged out. So, think of Fourier modes. This picture is very important. So, this is a Fourier space spheres. So, when I coarse grain it, so we have, when I coarse grain it, this yellow region will be averaged out. What do I mean by that? Imagine some signal is made up many waves, right. This is what Fourier means. Now, when I coarse grain it, what will happen to these guys? Small waves. If I coarse grain it at this level, so this will be going away, no. So, of course, amplitude of this signal, we basically look at these modes only, the lower modes are taken off. Of course, this mode may be interacting with these modes. Okay. So, there are nonlinear interaction of these modes with that mode, but that is what we need to take into account. These interactions, how are they affecting the parameters, but when you average out, these modes are gone. So, it corresponds to so these are, you can imagine 3D modes. So, when average out, this yellow shell is to be taken off, and what survives after averaging is phi less in coarse graining. Okay. And after coarse graining, we need to make this blue sphere bigger. We need to make the blue sphere go back to its original size. Means I am going to expand the blue sphere to lambda naught. So, in Fourier space, that is what would it imply. In real space, I am shrinking the size. In Fourier space, I will be cutting down those modes. These bigger things will be bigger spheres are taken off. Okay. So, we write down phi field as phi of x is phi less of x plus phi greater of x, and your idea is to retain only phi less x and average out phi greater. Okay. But it is not that you simply drop them off. So, my free energy was function of those parameters. No, I had R naught, C naught, U naught. Remember that phi 4 theory. Now, when I take these fields out, these parameters will be a different number. Okay, that will become, in fact, we call it R less, C naught less, U naught less. So, after my operation of coarse graining, my parameters would have changed. In fact, I am going to demonstrate how it has changed. Okay. So, this is a partition function. Now, partition function after this operation is well, we have both this phi less phi greater. No, I mean, remember I had this integral of all the modes, but we want to average out phi greater. So, this I want to basically write in terms of d phi less. The modes which survives are d phi less. Remember, when I wrote the partition function, I was integrated all phi 1, d phi 2, d phi 3 like this. So, what will survive is only d phi less. This is a description of coarse grained system, but my S, this is the free energy of this partition function Z. Now, of course, function of phi less, but this S this free energy, the parameters would have changed. Some would have changed, not all of them. Some parameter would have changed under this operation. This is a reduction operation, and this is what Wilson did it carefully, okay, and this is what I will describe how to do it for 5-4 theory. Okay. So, finally, I have this exponential of S stuff. Okay. Now, so this is my partition function. Okay. So, I need to basically compute partition function for this sphere first. You should have only phi less variables, no phi greater variables, okay, but it should capture all the physics. So, imagine I had this big spins, the interaction, I should have those interactions J1, well not J1 would be after rescaling, but I first do it by coarse graining J1 bar, we will do the rescaling after that. Okay. So, let us write down, I mean let us get slightly deeper into the procedure. It is definitely highly mathematical and reasonably complex, but you have to just pay attention what is being done. Okay. So, after coarse graining my variables are only phi less, right, phi greater is washed out. My new variables are, so these my free energy, well these terms did not exist in the before in the previous avatar, but after coarse graining maybe there will be terms like K4, K6, earlier I had only grad phi squared, no. So, that will correspond to K squared, but under this operation we may have new terms, we do not know, I mean there could be new terms. So, these are new terms which are possible, linear terms. So, this corresponds to grad phi to the power 4, right, 4 will give us K4, this is grad phi to the power 6, and these are all quadratic terms, well sorry I am not, I am making a mistake, grad square phi squared. So, this, so my phi is only 2 of them, phi minus k, phi k, these are quadratic terms in phi. In the nonlinear term, so phi 4 term, what will phi 4 term give in Fourier space? It is a convolution, and this is a convolution phi k1, phi k2, phi k3, phi k4, and I sum over all the modes. So, this is my nonlinear term. I could have some more nonlinear term, okay, I am not writing it here. It turns out we can, for phi 4 theory, these terms will not, they will go to 0. I will show you some terms will go to 0 under RG. We need this one, we need this one, and we need this one. Okay, this shown by Wilson. Okay, that is, this why is remarkable theory. Okay, so in final theory, we should require only a finite number of terms. If you require infinite number of terms, then this theory is non-renormalizable. Okay, so all the good theories of physics are supposed to be renormalizable theories. Well, gravity is a problem, that is why it is called non-renormalizable, but electrodynamics and nuclear forces can be written in terms of finite number of modes. Okay. So, these are so this is a property of renormalization theory, that you need only finite number of terms under scaling. Okay. So, and step 2 is rescaling. So, that is how does it look like. So, well let us look at some simple properties which we need. So, this is my original. So, here my variables are these block cross variables. Okay. When I do rescaling, I basically bring down the scale to this grid. So, what I am doing? I am writing my x prime variable for this box, which is x by b. Here right now b is 4. Is that clear to everyone? So, I am compressing it. So, my what was unit 16 will become 4, 4 will become 1. Okay. So, that is what we got. So, my integral, so by the way this integral must be the same, these two integrals must be the same under this operation. Okay. My free energy should give me the same number under this operation. Okay. So, we our in the at this level in the before scaling, my variables are phi less, c less, c4 less and so on, but after rescaling it is r prime, c prime, c4 prime like that. Okay. And my variable from phi less, it has become phi prime. Okay. Now, some interesting observation, it turns out, which we will do it later, the c less and c prime are unchanged. Okay. C less and C prime are unchanged. So, you can just take my word for it. So, here, so I want this integral and this integral must be the same value integral. No? Well, let us right now forget about C prime being equal to C less, but when I want this integral to be less same. So, I get C less. What will this give us? X d dx is a d dimensional integral. So, it will give me x to the power d, no. If it is radius, then r to the power d. I am just writing this x to the power d, okay, radius. Now, grad is 1 by length square. So, I just write as grad square and this phi less squared. Okay. I am just writing this integral here. You should think of x as a radius. Now, what about this integral? This is x prime to the power d, right, this guy. C prime is here, grad prime squared, phi prime squared. Now, what does x to the d by grad square multiplied by grad square will give you? Is radius to the power d minus 2. Okay. This object will give you r prime to the power d minus 2. What is the ratio of the two? R prime by r is b, right, r prime by r is 1 by b. Okay. So, just substitute it there and assume C less is equal to C prime. Okay. It turns out C does not change. So, I am going to show it later, okay. Just you have to bear with me. Then, so I am writing phi prime by phi less. So, you take this to the left hand side, phi prime by phi less squared and you get x by x, I get x to the power d minus 2 divided by x prime to the d minus 2. What will that give you? X by x prime is b, b to the power d minus 2. Okay. So, this is the property for the variables. How does variable scale or how does variable change under scaling? Is that clear to everyone? Okay. Now, you have to follow the same logic. Now, what about R? Now, by the way, we have now how does the field change? This C and C prime being equal gives you the scaling of the fields. By the way, this is very important, field scaling. Now, we can use this to find how R less and R prime are related. What will I do? Let us just do it quickly. R less x to the power d phi less squared equal to R x prime to the power d phi prime to the power squared. Okay. Yes. So, R less equal to R x prime by x to the power d, what will that be? 1 by b to the power d. Okay. And what is phi prime by phi less to the power d? It is going to be b to the power d minus 2, right. I just replace it here. So, b to the power d, b to the d cancel. So, r b minus 2. So, r less must be equal to, is the next slide, okay, yeah, here. So, I am just doing the algebra here, r less, well, I had put r less equal to r prime b minus 2. So, this is how we prove it. So, under scaling this parameter r will transform like that. Okay. You can apply the same logic, C prime I will not discuss it, C prime will go b minus 2 C, so C4 less. Now, that is what, when b is going bigger and bigger, so what happens to C4 prime? Decreases, right. So, it keeps decreasing. So, that is why it goes to 0. So, that is why we do not need the grad square squared. Okay. you can show that C6 will also go to 0 in the same manner, but R prime is increasing, you see R prime is increasing. So, R is important variable, and we can also apply exactly same logic, and you can show how does U prime and U less are related. U prime is U less to the power of multiplied by B to the 4 minus D. Okay. So, what does it mean? For D greater than 4, this will become small, right. Put D equal to 5, it is 1 by B. So, for D greater than 4, B U prime goes to 0. So, that is why you might have heard for dimension greater than 4, the nonlinear term is not very important in phase transition. Okay. The origin is this scaling formula. We can also talk about U6, U6 will go like that. So, it turns out for D greater than 3, U6 will go to 0. So, 3 and beyond, well, beyond 3 this is not relevant, and H we can follow the same logic, H prime goes like that. It turns out H will be important for all dimension. Okay, we can see that D equal to 1 also important, D equal to 2. So, this field variable, external field variable H is important. So, that is why we need to worry about R prime and H prime. Okay. These only under scaling, but coarse graining what happens is not covered here. Coarse graining we need to study how the this one effect only. So, coarse graining effect has to be studied, and that is a more complicated calculation.